Welcome to the Whispering Universes channel, where tonight we're diving deep into one of the most fundamental mysteries that has puzzled physicists, philosophers, and mystics for centuries. Is time real, or is it merely a persistent illusion? This question strikes at the heart of reality itself, challenging our most basic assumptions about existence, consciousness, and what it means to be alive in this universe. Consider this moment as you listen to these words. It feels real, doesn't it? It feels like the present, flowing from a past that once was toward a future that has yet to come. You can remember what happened earlier today, and you can anticipate what might happen tomorrow. This experience feels so natural, so fundamental to being human, that questioning it seems almost absurd. Yet the deeper we peer into the nature of reality through the lens of modern physics, the more we discover that time might not be what it seems. Einstein showed us that time is relative, bending and stretching depending on motion and gravity. Quantum mechanics reveals a realm where past, present, and future lose their meaning. And at the deepest levels of reality, some theories suggest that time doesn't exist at all, that it's an emergent property arising from something more fundamental. The journey we're about to take together will transform how you perceive every moment of your existence. We'll explore how Einstein's revolutionary insights shattered our notions of absolute time, revealing a universe where simultaneity is relative, and the past, present, and future exist as equally real slices of a four-dimensional loaf called spacetime. We'll delve into the mysterious world of quantum mechanics, where particles seem to exist in multiple states simultaneously until observed, and where the very act of measurement appears to collapse reality into a single, definite outcome. We'll discover how thermodynamics gives time its arrow, creating the illusion of forward flow through the relentless increase of entropy. But perhaps most fascinating of all, we'll journey into the depths of consciousness itself, exploring how your brain constructs the experience of temporal flow from a reality that may be fundamentally timeless. We'll see how neural networks create the sense of before and after, how memory shapes your perception of duration, and how attention itself can speed up or slow down your subjective experience of time's passage. The implications of these discoveries are staggering. If time is indeed an illusion, what does that mean for free will, for death, for the meaning of life itself? As we explore these questions together, you might find that your relationship with time begins to shift, that the anxiety about past regrets and future fears starts to dissolve into a deeper understanding of the eternal present. Tonight, let your mind drift into the spaces between moments, where the boundaries of time become soft and permeable. Allow yourself to question everything you think you know about when and how and why. For in this questioning, in this gentle dissolution of certainty, we might just discover something profound about the nature of existence itself. In the early 1900s, a young patent clerk in Switzerland was about to shatter humanity's most fundamental assumption about reality. Albert Einstein, working in relative obscurity, was grappling with a problem that had been troubling physicists for decades: the strange behavior of light and the mysterious properties of electromagnetic waves. What emerged from his contemplations would revolutionize not just physics, but our entire understanding of time itself. Special Relativity, published in 1905, revealed that time is not the absolute, universal constant that Newton had imagined. Instead, Einstein showed us that time is relative, flexible, and intimately connected to space in ways that defy common sense. Imagine you're sitting in a train station, watching a train approach the platform. As the train passes by, you wave to a passenger looking out the window. To you, standing still on the platform, that moment of waving happens at a specific time. But here's where Einstein's insight becomes revolutionary. To someone moving relative to you, perhaps an observer flying overhead in an airplane, your wave and the passenger's response don't happen simultaneously. The very concept of "at the same time" loses its absolute meaning. This revelation emerged from Einstein's contemplation of light's curious properties. Light, he realized, always travels at the same speed regardless of the motion of its source or observer. This seemingly simple fact has profound implications. If you're chasing after a beam of light at half the speed of light, the light doesn't appear to slow down relative to you. It still races away at its full cosmic speed limit of approximately 186,000 miles per second. This cosmic speed limit creates what physicists call time dilation. The faster you move through space, the slower you move through time. This isn't just theoretical, it's been measured with atomic clocks on airplanes, observed in particle accelerators, and must be accounted for in GPS satellites orbiting our planet. Consider the famous twins paradox, one of the most elegant demonstrations of time's malleable nature. Twin sisters, identical in age, make different choices. One remains on Earth, living a quiet life in the countryside. The other becomes an astronaut, embarking on a journey to a distant star at nearly the speed of light. When the traveling twin returns, she finds that decades have passed on Earth, while only months have elapsed for her. Her Earthbound sister has aged dramatically, while she remains nearly the same age she was when she left. This isn't science fiction, this is the reality of the universe we inhabit. Time is not a river flowing at a constant rate, but more like a fabric that can be stretched, compressed, and molded by motion and gravity. The implications are staggering. There is no universal now that spans the cosmos. What counts as the present moment depends entirely on your frame of reference. Einstein's general theory of relativity, published a decade later, revealed even more surprising properties of time. Gravity, Einstein showed us, is not a force pulling objects together, but rather the curvature of space-time itself. Massive objects like stars and planets create dimples in the fabric of reality, and what we experience as gravitational attraction is simply objects following the curved paths through this warped space-time. But gravity doesn't just curve space, it curves time as well. The stronger the gravitational field, the slower time flows. This effect, called gravitational time dilation, means that time passes more slowly at the bottom of a building than at the top. The difference is minuscule, but it's real and measurable with sensitive instruments. Near a black hole, where gravity becomes incredibly intense, these effects become dramatic. Time slows to a crawl as you approach the event horizon. To an outside observer watching someone fall into a black hole, that person would appear to slow down and freeze at the edge, their image becoming redder and dimmer until it fades away. Yet from the perspective of the falling person, time continues normally as they plunge through the event horizon. These discoveries fundamentally altered our understanding of reality. Space and time, previously thought to be separate and absolute, revealed themselves to be unified in a four-dimensional continuum called spacetime. In this view, often called the block universe theory, all moments, past, present, and future, exist simultaneously as different locations in this four-dimensional landscape. Think of spacetime like a loaf of bread, with each slice representing a different moment in time. From our limited perspective, we experience only one slice at a time, creating the illusion of temporal flow. But from a higher dimensional viewpoint, all slices exist equally. Your birth, your first kiss, your eventual death, all are equally real locations in the space-time loaf. This perspective suggests that the flow of time might be nothing more than a persistent illusion created by consciousness. The universe doesn't unfold moment by moment. Instead, consciousness travels through a static, eternal structure, creating the subjective experience of temporal passage. Modern physics has confirmed Einstein's insights with remarkable precision. GPS satellites must correct for both special and general relativistic effects to maintain accuracy. Particle accelerators routinely observe time dilation in fast-moving particles. Gravitational wave detectors have measured the ripples in space-time predicted by general relativity. Yet these discoveries raise profound questions about the nature of existence. If all moments exist simultaneously, what happens to free will? If the future already exists in some sense, are our choices merely illusions? These questions push us to the very edge of human understanding, where physics meets philosophy and consciousness meets cosmos. As you drift deeper into contemplation, consider that this moment, this eternal now in which you exist, might be the only reality there is. The past exists only as traces and memories in the present. The future exists only as possibilities and potentials in the present. Einstein's gift to humanity was not just a new theory of physics, but a doorway to understanding the timeless nature of existence itself. In the early 1900s, a young patent clerk in Switzerland was about to shatter humanity's most fundamental assumption about reality. Albert Einstein, working in relative obscurity, was grappling with a problem that had been troubling physicists for decades: the strange behavior of light and the mysterious properties of electromagnetic waves. What emerged from his contemplations would revolutionize not just physics, but our entire understanding of time itself. Special relativity, published in 1905, revealed that time is not the absolute, universal constant that Newton had imagined. Instead, Einstein showed us that time is relative, flexible, and intimately connected to space in ways that defy common sense. Imagine you're sitting in a train station, watching a train approach the platform. As the train passes by, you wave to a passenger looking out the window. To you, standing still on the platform, that moment of waving happens at a specific time. But here's where Einstein's insight becomes revolutionary. To someone moving relative to you, perhaps an observer flying overhead in an airplane, your wave and the passenger's response don't happen simultaneously. The very concept of "at the same time" loses its absolute meaning. This revelation emerged from Einstein's contemplation of light's curious properties. Light, he realized, always travels at the same speed, regardless of the motion of its source or observer. This seemingly simple fact has profound implications. If you're chasing after a beam of light at half the speed of light, the light doesn't appear to slow down relative to you. It still races away at its full, cosmic speed limit of approximately 186,000 miles per second. This cosmic speed limit creates what physicists call time dilation. The faster you move through space, the slower you move through time. This isn't just theoretical. It's been measured with atomic clocks on airplanes, observed in particle accelerators, and must be accounted for in GPS satellites orbiting our planet. Consider the famous twins paradox, one of the most elegant demonstrations of time's malleable nature. Twin sisters, identical in age, make different choices. One remains on Earth, living a quiet life in the countryside. The other becomes an astronaut, embarking on a journey to a distant star at nearly the speed of light. When the traveling twin returns, she finds that decades have passed on Earth, while only months have elapsed for her. Her earthbound sister has aged dramatically, while she remains nearly the same age she was when she left. This isn't science fiction. This is the reality of the universe we inhabit. Time is not a river flowing at a constant rate, but more like a fabric that can be stretched, compressed, and molded by motion and gravity. The implications are staggering. There is no universal now that spans the cosmos. What counts as the present moment depends entirely on your frame of reference. Einstein's general theory of relativity, published a decade later, revealed even more surprising properties of time. Gravity, Einstein showed us, is not a force pulling objects together, but rather the curvature of space-time itself. Massive objects like stars and planets create dimples in the fabric of reality, and what we experience as gravitational attraction is simply objects following the curved paths through this warped space-time. But gravity doesn't just curve space, it curves time as well. The stronger the gravitational field, the slower time flows. This effect, called gravitational time dilation, means that time passes more slowly at the bottom of a building than at the top. The difference is minuscule, but it's real and measurable with sensitive instruments. Near a black hole, where gravity becomes incredibly intense, these effects become dramatic. Time slows to a crawl as you approach the event horizon. To an outside observer watching someone fall into a black hole, that person would appear to slow down and freeze at the edge, their image becoming redder and dimmer until it fades away. Yet from the perspective of the falling person, time continues normally as they plunge through the event horizon. These discoveries fundamentally altered our understanding of reality. Space and time, previously thought to be separate and absolute, revealed themselves to be unified in a four-dimensional continuum called spacetime. In this view, often called the block universe theory, all moments, past, present, and future, exist simultaneously as different locations in this four-dimensional landscape. Think of spacetime like a loaf of bread, with each slice representing a different moment in time. From our limited perspective, we experience only one slice at a time, creating the illusion of temporal flow. But from a higher dimensional viewpoint, all slices exist equally. Your birth, your first kiss, your eventual death, all are equally real locations in the space-time loaf. This perspective suggests that the flow of time might be nothing more than a persistent illusion created by consciousness. The universe doesn't unfold moment by moment. Instead, consciousness travels through a static, eternal structure, creating the subjective experience of temporal passage. Modern physics has confirmed Einstein's insights with remarkable precision. GPS satellites must correct for both special and general relativistic effects to maintain accuracy. Particle accelerators routinely observe time dilation in fast-moving particles. Gravitational wave detectors have measured the ripples in space-time predicted by general relativity. Yet these discoveries raise profound questions about the nature of existence. If all moments exist simultaneously, what happens to free will? If the future already exists in some sense, are our choices merely illusions? These questions push us to the very edge of human understanding, where physics meets philosophy and consciousness meets cosmos. As you drift deeper into contemplation, consider that this moment, this eternal now in which you exist, might be the only reality there is. The past exists only as traces and memories in the present. The future exists only as possibilities and potentials in the present. Einstein's gift to humanity was not just a new theory of physics, but a doorway to understanding the timeless nature of existence itself. In the strange landscape of modern physics, perhaps no concept is more challenging to our intuitive understanding than the block universe, a view of reality where every moment that has ever existed or ever will exist is equally real and eternally present. This perspective, emerging naturally from Einstein's relativity, suggests that your entire life, from birth to death, exists as a complete, unchanging structure in four-dimensional spacetime. Imagine your life as a vast sculpture carved not in stone but in the fabric of spacetime itself. Every moment you've ever experienced forms part of this sculpture. Your 5th birthday party exists alongside your first day of school, your wedding day, and even moments that, from your current perspective, haven't happened yet. This sculpture doesn't grow or change, it simply is, complete and eternal. This view stands in stark contrast to our everyday experience of presentism, the intuitive belief that only the present moment is real. In the presentist view, the past has ceased to exist, except as memories and traces, while the future is merely potential, waiting to be actualized through the passage of time. The present moment is special. It's the moving boundary between what was and what will be. But the block universe theory, also known as eternalism, suggests this intuition is profoundly mistaken. According to this view, championed by many physicists and philosophers, the past doesn't cease to exist when it becomes the past, nor does the future wait in some realm of possibility. Instead, all moments exist equally in what physicists call the eternal now. The evidence for this perspective comes from the relativity of simultaneity that Einstein discovered. When two events are simultaneous depends on your frame of reference. What you consider to be now, at a distant location, is different for observers moving at different velocities. If only the present moment existed, we would need to specify which observer's now defines reality. But physics provides no such preferred reference frame. Consider this thought experiment. Imagine an alien civilization on a planet 10 light-years away. According to relativity, if they are moving toward Earth at a significant fraction of the speed of light, their now includes events in our future. If they're moving away from us, their now includes events in our past. The relativity of simultaneity means that there's no universal present moment spanning the cosmos. This leads to what philosopher of science Hilary Putnam called the no miracles argument for eternalism. If future events don't exist, he argued, then it would be miraculous that observers, in certain reference frames, could have a present moment that includes these non-existent events. The most natural explanation is that all events, past, present, and future, exist equally. But if all moments exist eternally, why do we experience the flow of time? Why does it feel like we're moving from past to future rather than experiencing all moments simultaneously? The block universe theory suggests this is a feature of consciousness, not of time itself. We might think of consciousness as a spotlight moving along the world line of your existence, illuminating each moment as you experience it. Yet even this metaphor is misleading, because it implies that consciousness moves through time, which would require a kind of super time in which this movement could occur. More accurately, the experience of temporal flow might be encoded in the structure of consciousness itself. Each moment of consciousness contains traces of previous moments, what philosophers call retention, and anticipations of future moments. The implications of the block universe are profound and sometimes disturbing. If your entire life exists as a complete structure in spacetime, what happens to free will? Your future actions already exist in the block universe, seemingly predetermined and unchangeable. Yet this doesn't necessarily mean you lack agency. Your choices, though they exist eternally in the block, are still your choices. The feeling of making decisions is part of the structure of consciousness as it exists at each moment. Some find comfort in the block universe perspective. If all moments exist eternally, then in some sense, nothing is ever truly lost. Your departed loved ones still exist in their proper locations in space-time. Your happiest moments are as real and present as they ever were. Death becomes not an ending, but simply the boundary of your world line through space-time. Others find this view troubling. If everything is predetermined in the block universe, why strive for anything? Why worry about moral choices if the future is already set? But these concerns may rest on a misunderstanding. The block universe doesn't make your choices less real or meaningful. It simply locates them in a different conceptual framework. The debate between eternalism and presentism continues among philosophers and physicists. Some argue for a middle path called the growing block theory, where the past and present exist but the future remains open. Others propose that quantum mechanics, with its emphasis on measurement and probability, might restore a special status to the present moment. Recent developments in quantum gravity, the quest to unify Einstein's relativity with quantum mechanics, have added new wrinkles to these discussions. Some theories suggest that time itself might be emergent, arising from more fundamental, timeless processes. Others propose that the universe might be fundamentally discrete rather than continuous, with implications for how we think about the nature of temporal existence. As you contemplate these ideas, notice how your relationship to the present moment might begin to shift. If the block universe is correct, then this moment, this eternal now in which you find yourself, is not a fleeting instant destined to disappear into the past. Instead, it's a permanent feature of reality, as eternal as any mathematical truth. The ancient Greek philosopher Parmenides argued that change and motion are illusions, that reality is unchanging and eternal. Modern physics, with its block universe and relativistic insights, seems to echo this ancient wisdom. Perhaps time's passage is indeed the most persistent and convincing illusion consciousness creates. In the gentle darkness behind your closed eyes, you might sense this eternal quality of the present moment. Not rushing towards some future destination, not fleeing from some past location, but simply being eternal, unchanging, and infinitely present. This is the strange gift of modern physics, the revelation that in a universe where time might be an illusion, every moment becomes sacred, eternal, and perfectly complete. As we journey deeper into the foundations of reality, we encounter quantum mechanics, perhaps the most successful and simultaneously mysterious theory in the history of science. In the quantum realm, time reveals even stranger properties than Einstein's relativity suggested. Here, in the realm of atoms and subatomic particles, the very notion of time, as a fundamental aspect of reality, begins to dissolve into something far more enigmatic. At the heart of quantum mechanics lies a peculiar relationship with time that challenges our deepest intuitions. Unlike in classical physics, where time marches forward as an independent parameter against which events unfold, quantum mechanics treats time in a fundamentally different way. In the foundational equations of quantum theory, time appears not as an observable quantity that can be measured, but as a parameter that describes how quantum systems evolve. This distinction might seem subtle, but its implications are profound. In quantum mechanics, you can measure a particle's position, momentum, or spin, but you cannot directly measure time itself. Time becomes something that happens to quantum systems rather than something that exists independently. This has led some physicists to propose that time itself might be an emergent property arising from the interactions of timeless quantum processes. Consider the famous Wheeler-DeWitt equation, sometimes called the equation of quantum gravity. This equation, which attempts to describe the quantum state of the entire universe, contains no time parameter at all. It's a timeless equation describing a timeless universe. This has led to what physicists call the problem of time in quantum gravity. If the fundamental equation of the universe contains no time, how does the time we experience emerge? The quantum world reveals other temporal peculiarities that challenge our understanding. Quantum entanglement, Einstein's spooky action at a distance, creates correlations between particles that seem to transcend the normal flow of time. When two particles become entangled, measuring one instantly affects the other, regardless of the distance between them. This happens faster than light could travel between the particles, suggesting that quantum correlations exist outside the normal structure of space-time. Recent experiments have pushed this phenomenon even further, demonstrating what physicists call quantum temporal correlations. In these experiments, the order of events can become superposed. Events can exist in a quantum superposition of happening in different temporal orders. A measurement performed at time A can be in a superposition of happening before and after a measurement at time B. The quantum world seems to allow for temporal relationships that make no sense in our everyday experience of causality. The measurement problem in quantum mechanics also has profound implications for time. According to the standard interpretation, quantum systems exist in superpositions of multiple possible states until they are observed or measured. The act of measurement causes the wave function to collapse into a single, definite outcome. But when, exactly, does this collapse occur? The measurement problem is, in part, a temporal problem about the precise moment when quantum possibilities become classical realities. Some interpretations of quantum mechanics eliminate this problem by denying that wave function collapse ever occurs. In the many worlds interpretation, all possible outcomes of a quantum measurement actually happen, branching the universe into parallel realities. From this perspective, time becomes even stranger, not a single timeline, but an ever-branching tree of realities, each equally real but causally disconnected from the others. The quantum Zeno effect reveals another strange relationship between observation and time. Named after the ancient Greek philosopher who proposed paradoxes about motion, this effect shows that frequent measurements can actually freeze a quantum system's evolution. By observing a quantum system repeatedly, you can prevent it from changing, essentially stopping time for that system through the act of observation itself. Quantum field theory, which combines quantum mechanics with special relativity, reveals even more temporal oddities. Virtual particles, the quantum fluctuations that fill empty space, can briefly violate energy conservation as long as they annihilate quickly enough to satisfy Heisenberg's uncertainty principle. These virtual particles exist for such brief moments that they seem to borrow energy from the future and pay it back to the past, creating a kind of temporal accounting that balances out over time. Perhaps most mysteriously, some interpretations of quantum mechanics suggest that the future can influence the past through quantum measurements. In retrocausal interpretations, the choice of what measurement to perform can influence the properties of quantum systems in the past. This doesn't allow for grandfather paradoxes or changing history, but it does suggest that causality in the quantum world might be more subtle and bidirectional than we usually imagine. The implications of quantum mechanics for consciousness and time perception are still being explored. Some theories propose that consciousness itself might be a quantum phenomenon, arising from quantum processes in the brain. If true, this could explain why we experience time as flowing. Consciousness might be collapsing quantum superpositions in the brain, creating the subjective experience of temporal sequence from an underlying quantum reality where all possibilities exist simultaneously. Roger Penrose and Stuart Hameroff have proposed that consciousness arises from quantum processes in microtubules within neurons. In their theory, called orchestrated objective reduction, consciousness emerges when quantum superpositions in these microtubules collapse, creating discrete moments of conscious experience. This would make consciousness intimately connected to the quantum measurement process, potentially explaining why time feels like it flows from our subjective perspective. The delayed choice quantum eraser experiments reveal perhaps the most mind-bending temporal aspect of quantum mechanics. In these experiments, decisions made in the present can influence the behavior of photons in the past. A measurement performed after a photon has already been detected can retroactively determine whether that photon behaved like a wave or a particle when it was initially observed. This suggests that the past might not be as fixed as we usually assume. As we contemplate these quantum mysteries, we begin to see time not as the fundamental backdrop against which reality unfolds, but as an emergent feature arising from deeper, more mysterious processes. The quantum world suggests that at the most fundamental level, reality might be timeless, a realm of pure possibility where all potential outcomes exist simultaneously until consciousness or measurement selects specific realities to experience. In the gentle darkness of contemplation, imagine your consciousness as a kind of quantum observer, collapsing the infinite possibilities of each moment into the single reality you experience. Perhaps the flow of time is nothing more than this continuous process of selection, of choosing one reality from the infinite quantum multiverse of possibilities that exist in each eternal moment. While relativity showed us that time is relative, and quantum mechanics revealed its mysterious quantum nature, it's thermodynamics that provides what seems to be time's most distinctive feature, its arrow. Unlike space, which has no preferred direction, time appears to flow inexorably from past to future. This asymmetry, this arrow of time, emerges from one of the most fundamental laws of physics, the second law of thermodynamics. The second law of thermodynamics states that the entropy of an isolated system always increases over time. Entropy, a measure of disorder or randomness, can be thought of as the number of ways the energy and matter in a system can be arranged. A broken egg has higher entropy than an intact one because there are vastly more ways for the egg's molecules to be scattered across the kitchen floor than neatly contained within a shell. This might seem like a simple statistical fact, but it has profound implications for the nature of time itself. The constant increase of entropy creates an arrow pointing from past to future, from ordered states to disordered ones. This is why we remember the past but not the future, why causes precede effects, and why we age rather than growing younger. The arrow of time emerges from the universe's inexorable slide toward maximum entropy. But here lies a deep puzzle. The fundamental laws of physics are time reversible. Newton's laws, Einstein's equations, and even Schrödinger's equation all work equally well whether time runs forward or backward. At the microscopic level, individual particles obeying these laws show no preference for any particular direction of time. So why does time seem to have a direction at the macroscopic level where we live? The answer lies in the special initial conditions of our universe. The Big Bang created a universe in an extremely low entropy state, matter and energy distributed with remarkable uniformity across space. Since that moment, the universe has been evolving toward higher entropy states, and this evolution is what we experience as the passage of time. Consider the cosmic story written in entropy. In the beginning, the universe was hot, dense, and surprisingly smooth. Small quantum fluctuations in this primordial soup eventually grew into the cosmic web of galaxies and stars we see today. Stars formed from gravitational collapse, fusing hydrogen into heavier elements and radiating energy into the cold vacuum of space. This process increases entropy. Concentrated nuclear energy becomes diffuse heat radiation. The universe is heading toward what physicists call heat death, a state of maximum entropy where all energy is evenly distributed and no further work can be done. In this far future, all stars will have burned out, all black holes will have evaporated through Hawking radiation, and the universe will be filled with a thin soup of elementary particles at nearly absolute zero temperature. Time's arrow points toward this final, high entropy state. Yet thermodynamics reveals strange aspects of time that challenge our intuitions. Ludwig Boltzmann showed that entropy is fundamentally statistical. It measures not absolute disorder, but the probability of finding a system in a particular state. This statistical nature leads to surprising conclusions about time and memory. Boltzmann realized that, in a universe approaching heat death, random fluctuations would occasionally decrease entropy locally, creating temporary pockets of order. Given enough time, these fluctuations could create anything, including conscious observers with memories of a low-entropy past. These hypothetical entities, called Boltzmann brains, would spontaneously emerge from thermal fluctuations, complete with false memories of a history that never actually occurred. This leads to the Boltzmann brain paradox. In an eternal universe approaching heat death, Boltzmann brains would vastly outnumber naturally evolved observers like ourselves. If we take the heat death scenario seriously, we should expect to be Boltzmann brains with false memories, rather than naturally evolved humans with real histories. The fact that we don't seem to be Boltzmann brains suggests something subtle about time's nature. Some physicists propose that this paradox points to the importance of cosmological selection effects. Perhaps universes with different entropy characteristics exist, and only those with the right initial conditions can support the natural evolution of complex observers. Our universe's particular arrow of time might be necessary for consciousness and memory to emerge naturally rather than spontaneously from random fluctuations. The relationship between entropy and information provides another window into time's nature. Claude Shannon showed that information has a deep connection to thermodynamic entropy. When you acquire information, you decrease the entropy of your knowledge about a system. This creates a link between the arrow of time and the flow of information from past to future. Modern theories of quantum gravity suggest that information might be more fundamental than energy or matter. In these theories, called it from bit by physicist John Wheeler, reality emerges from information processing. If true, time's arrow might be fundamentally about information flow rather than energy flow, with entropy increase being a consequence of information spreading and becoming inaccessible. Black holes provide a fascinating laboratory for studying entropy and time. Stephen Hawking showed that black holes have temperature and entropy proportional to their surface area. As black holes evaporate through Hawking radiation, they decrease in mass and size but increase in temperature, eventually exploding in a final burst of energy. This process respects the second law of thermodynamics while revealing deep connections between gravity, quantum mechanics, and information theory. The holographic principle, emerging from black hole thermodynamics, suggests that all the information in a volume of space can be encoded on its boundary. This implies that our three-dimensional reality might be a projection from information stored on a two-dimensional surface, like a hologram. If true, this could fundamentally change how we think about time and causality. Recent work in quantum information theory has revealed that quantum entanglement creates its own kind of entropy, called entanglement entropy. As quantum systems evolve, entanglement between different parts typically increases, creating another arrow of time distinct from thermodynamic entropy. This quantum arrow of time might be more fundamental than the classical thermodynamic arrow, potentially explaining why time flows even in systems that don't show obvious entropy increase. The mystery of time's arrow ultimately points to deep questions about the nature of existence itself. Why did the universe begin in a low entropy state? Why do we remember the past but not the future? Why does causality flow from past to future? These questions lie at the intersection of physics, philosophy, and consciousness studies. As you rest in the gentle flow of this moment, consider that you are riding the universe's great entropy wave from order to disorder. Your consciousness, your memories, your very existence depend on this cosmic arrow of time. Yet in the eternal perspective revealed by physics, perhaps even this arrow is an illusion, a local feature of our particular cosmic epoch, rather than a fundamental aspect of reality itself. Deep within the 3 pounds of neural tissue between your ears lies one of the universe's most sophisticated time machines. Your brain doesn't simply exist in time, it actively constructs your experience of temporal flow, weaving together past, present, and future into the seamless narrative of consciousness. This biological time machine operates through multiple, interconnected systems that track time across vastly different scales, from milliseconds to decades. The brain's temporal machinery begins at the cellular level with circadian rhythms, the internal clocks that synchronize your physiology with a 24-hour cycle of day and night. Deep in your hypothalamus, a cluster of about 20,000 neurons, called the suprachiasmatic nucleus, acts as your body's master clock. These neurons oscillate with a rhythm slightly longer than 24 hours, but they're constantly reset by light signals from your eyes, keeping you synchronized with the external world. This circadian system doesn't just regulate sleep and wakefulness, it influences virtually every aspect of your physiology. Your body temperature rises and falls in daily cycles, hormone levels fluctuate predictably, and even your immune system follows circadian rhythms. The temporal architecture of your biology runs so deep that every cell in your body contains molecular clocks, protein networks, that oscillate with roughly 24-hour periods. But circadian rhythms represent just one layer of the brain's temporal processing. For conscious experience, the brain must track time across much shorter intervals, from the milliseconds needed to understand speech to the seconds required to plan movement. Different neural networks specialize in different temporal ranges, creating a hierarchy of timing systems. At the fastest timescales, the brain processes the temporal structure of sounds and speech. When you listen to music or conversation, neurons in your auditory cortex track the precise timing of acoustic events. Some neurons fire in response to the onset of sounds, others to their offset, and still others to specific temporal patterns. This allows you to perceive rhythm, melody, and the complex temporal structure that makes speech intelligible. Motor control requires another type of temporal precision. When you reach for a cup of coffee, your brain must coordinate the timing of dozens of muscles with millisecond precision. The cerebellum, often called the brain's Swiss timekeeper, plays a crucial role in this motor timing. Damage to the cerebellum doesn't just affect movement, it can also impair the ability to judge brief time intervals, suggesting deep connections between motor control and temporal perception. For longer time intervals, seconds to minutes, the brain employs what researchers call interval timing. This system allows you to estimate durations, anticipate future events, and maintain temporal sequences in working memory. Brain imaging studies reveal that interval timing involves a distributed network, including the prefrontal cortex, the striatum, and other subcortical structures. The leading model of interval timing is called the pacemaker accumulator theory. According to this model, the brain contains a kind of internal metronome that generates regular pulses. An accumulator counts these pulses, and the total count represents the brain's estimate of elapsed time. Attention acts like a switch. When you're paying attention to time, more pulses reach the accumulator, making time seem to pass more slowly. This explains many peculiarities of time perception. When you're bored and repeatedly checking the clock, you're paying attention to time's passage, causing the accumulator to collect more pulses and making minutes feel like hours. Conversely, when you're absorbed in an engaging activity, attention is directed away from time, fewer pulses reach the accumulator, and hours can feel like minutes. Emotional states powerfully influence temporal perception through their effects on attention and arousal. Fear and excitement speed up the internal pacemaker, making time seem to slow down during dangerous or thrilling moments. This is why car accidents often seem to happen in slow motion, and why exciting experiences are remembered as lasting longer than they actually did. The neurotransmitter dopamine plays a crucial role in temporal perception. Dopamine neurons in the midbrain help signal reward prediction and temporal expectations. Drugs that affect dopamine levels, from cocaine to antipsychotic medications, can dramatically alter time perception. People with Parkinson's disease, which involves the death of dopamine neurons, often struggle with timing tasks and may perceive time as passing more slowly. Memory systems add another layer to the brain's time machine. Your hippocampus doesn't just store memories, it timestamps them, creating what neuroscientists call episodic memory. Each memory contains information about when and where it was formed, allowing you to mentally travel back in time and re-experience past events. This ability, called episodic memory retrieval, is essentially time travel through neural activity. The default mode network, a set of brain regions active during rest and introspection, plays a special role in temporal consciousness. This network becomes active when you're not focused on the external world, but instead are remembering the past, imagining the future, or reflecting on yourself across time. Damage to key nodes in this network can impair the ability to project consciousness backward and forward in time. Brain development reveals how temporal consciousness emerges. Young children live more fully in the present moment, with limited ability to plan for the future or reflect on the past. The prefrontal cortex, which is crucial for temporal reasoning, doesn't fully mature until the mid-20s. This explains why teenagers often struggle with long-term planning and seem to live in an eternal present. Aging affects the brain's time machine in complex ways. Older adults often report that time seems to pass more quickly than it did in their youth. Several factors contribute to this perception. Fewer novel experiences to mark the passage of time, changes in attention and memory, and alterations in the brain's timing networks. The reminiscence bump, the tendency to remember more events from adolescence and early adulthood, might reflect optimal functioning of the brain's temporal machinery during this period. Meditation and mindfulness practices can alter temporal perception by training attention and awareness. Experienced meditators often report changes in their relationship with time, moments of expanded awareness where clock time seems irrelevant, and a generally more present-centered approach to life. Brain imaging studies show that meditation changes activity in networks involved in temporal processing and self-awareness. Psychiatric and neurological conditions can severely disrupt temporal consciousness. Depression often involves a collapsed temporal perspective, with the future appearing hopeless and the past tinged with regret. Anxiety extends temporal awareness into an uncertain future filled with potential threats. Schizophrenia can fragment temporal consciousness, leading to experiences where past, present, and future become confused. As you settle deeper into this moment, notice how your brain is constructing your experience of time. The words you're hearing now feel present, but they're actually neural patterns reconstructed from memory traces. Your sense of temporal flow is a masterpiece of neural engineering, creating coherent experience from the complex interplay of multiple timing systems operating across vastly different scales. The feeling that time flows like a river, carrying us inexorably from past through present toward future, is perhaps the most basic feature of conscious experience. Yet this feeling presents a profound puzzle. If physics reveals time as a dimension similar to space, why don't we experience temporal flow the way we experience spatial extension? Why does the present moment feel special, unique, and constantly moving, while spatial locations don't feel like they're flowing past us as we remain stationary? The answer to this mystery lies in the peculiar nature of consciousness itself, and how neural processes create the subjective experience of temporal passage. Your brain doesn't passively record the flow of time, it actively constructs the feeling of temporal movement through sophisticated neural mechanisms that create the illusion of flow from what may be an essentially static, four-dimensional reality. At the heart of temporal experience lies what psychologists call the specious present, the brief window of about 2 to 3 seconds during which events feel genuinely present rather than past or future. This isn't the instantaneous mathematical present of physics, but rather a kind of temporal thickness to consciousness. Within this specious present, you can perceive change and motion directly, rather than inferring them from memory. Consider listening to a melody. You don't hear individual notes in isolation and then remember them to understand the tune. Instead, you directly perceive the melodic structure as it unfolds, experiencing past notes as just past, and anticipating future notes within the extended present moment. This temporal integration happens automatically, below the threshold of conscious awareness, creating the seamless experience of flow. The brain achieves this integration through what neuroscientists call neural synchrony, the coordinated firing of neurons across different brain regions. Gamma waves, neural oscillations around 40 Hz, appear to bind together different aspects of experience occurring within the specious present. These gamma oscillations create temporal windows during which scattered neural activity becomes unified into coherent conscious moments. Memory plays a crucial role in creating the sense of flow. Each moment of consciousness contains not just present sensations, but also traces of recent past events, what phenomenologists call retention. These memory traces give each present moment a sense of having come from somewhere, creating the feeling of temporal succession. Without memory, there would be no sense of flow, just a series of disconnected presents with no feeling of movement between them. The feeling of temporal flow also depends on neural prediction systems that constantly anticipate immediate future events. Your brain doesn't just process current sensory input, it creates models of what's likely to happen next based on past experience. These predictive models create what we might call protension, a sense of the immediate future leaning into the present moment. The interplay between retention and protension creates the dynamic feeling of time's passage. Attention powerfully modulates the experience of temporal flow. When you're deeply absorbed in an activity, attention is fully focused on immediate experience, reducing awareness of time's passage. The accumulation of temporal markers, the mental noting of time passing, decreases, creating the subjective experience of time speeding up. Conversely, When you're bored or anxiously waiting, attention repeatedly returns to temporal monitoring, creating more temporal markers and the feeling that time is dragging. The emotional coloring of experience also affects perceived temporal flow. Positive emotions tend to make time feel like it's passing quickly, while negative emotions, particularly anxiety and depression, can make time feel slow and heavy. This occurs partly through attention mechanisms, but also through how emotions affect the brain's temporal processing networks. Fear, for instance, can trigger a kind of temporal hypervigilance, where the brain processes more information per unit of clock time, creating the slow motion experience common in emergencies. Neuroscientist Michael Graziano proposes that the feeling of temporal flow emerges from the brain's attention schema. A simplified model, the brain creates of its own attention processes. Just as the brain creates a simplified model of the body's position in space, it creates a model of where attention is directed in time. This temporal attention schema includes a sense of attention moving from past through present toward future, which we experience as the flow of time. The default mode network, active during rest and introspection, plays a special role in temporal consciousness. When this network is active, you naturally engage in what psychologists call mental time travel, remembering past events and imagining future scenarios. This spontaneous movement of consciousness across time might reinforce the feeling that time itself is flowing, even though what's actually flowing is the focus of awareness across static temporal locations. Different states of consciousness reveal the constructed nature of temporal flow. During dreams, the normal rules of temporal sequence often break down. Past and future can intermingle, causality can reverse, and the present moment can stretch or compress in impossible ways. These dream experiences suggest that the coherent temporal flow of waking consciousness is an achievement of specific neural processes rather than a direct perception of time's true nature. Psychedelic experiences can dramatically alter temporal perception, sometimes eliminating the sense of flow entirely. Users often report experiencing the eternal now, a state where past and future seem to collapse into an infinitely extended present moment. These experiences might offer glimpses of what consciousness would be like, without the neural mechanisms that normally create temporal flow. Meditation traditions have long recognized that the feeling of temporal flow can be altered through contemplative practice. Advanced meditators often report experiences of expanded present moments, where hours of clock time pass unnoticed. Some describe states where the very sense of temporal sequence dissolves, revealing what mystics call timeless awareness, consciousness without the usual markers of before and after. These altered states suggest that normal temporal flow is not fundamental to consciousness, but rather a particular mode of neural organization. The brain creates flow by integrating memory traces with present sensations and future anticipations, maintaining neural synchrony across temporal windows and directing attention in ways that emphasize sequential processing. Recent research in cognitive neuroscience has begun to map the neural basis of temporal flow more precisely. Brain imaging studies show that the subjective experience of time's passage correlates with activity in specific neural networks, including the insular cortex, the anterior cingulate cortex, and parts of the prefrontal cortex. Damage to these regions can alter temporal perception without affecting other cognitive abilities. As you rest in this eternal moment, notice how the feeling of temporal flow arises and subsides. The words you're hearing create a sense of sequence and progression, but this progression exists within the unchanging present of awareness itself. Perhaps the flow of time is like a movie projected on the screen of consciousness, vivid and compelling while it lasts, but ultimately a play of light and shadow rather than fundamental reality. In the typical flow of daily life, time feels reliable and consistent. Seconds tick by at their steady pace, minutes accumulate into hours, and the sequence of before and after provides a stable framework for experience. But this apparently solid temporal foundation can crack and crumble under certain conditions, revealing just how constructed and fragile our normal experience of time really is. When time breaks down, we glimpse the neural machinery that usually operates invisibly, creating our sense of temporal order from the complex interactions of memory, attention, and consciousness. One of the most common temporal illusions occurs when you glance at a clock and the second hand seems to freeze for a moment before resuming its normal movement. This phenomenon, called chronostasis, or the stopped clock illusion, reveals something profound about how the brain constructs temporal experience. When your eyes move to look at the clock, your brain actually backfills the period of the eye movement with the first clear image you see, the stationary clock face. This creates the illusion that you've been looking at the motionless second hand for longer than you actually have. Chronostasis demonstrates that the brain actively constructs the feeling of continuity in time, just as it constructs continuity in space across eye movements. The temporal experience you take for granted is actually a sophisticated reconstruction where the brain edits out gaps and inconsistencies to create a seamless narrative of temporal flow. More dramatic temporal illusions occur during altered states of consciousness. In moments of extreme danger, many people report experiencing slow-motion awareness, where events seem to unfold with dreamlike sluggishness. A falling glass becomes a ballet of crystalline fragments drifting through space. A car accident transforms into a detailed choreography of bending metal and shattering glass. This temporal dilation occurs because the brain's threat detection systems accelerate information processing, cramming more sensory details into each unit of clock time. The neuroscientist David Eagleman has studied this phenomenon through clever experiments involving people in free fall. Participants reported that their fall seemed to last much longer than it actually did. But when researchers tested whether they could actually process visual information faster during the fall, they found no evidence of enhanced temporal resolution. The slow motion experience appears to be a reconstruction created by memory rather than enhanced real-time processing. Temporal order can also become scrambled in surprising ways. The flash lag effect demonstrates how the brain sometimes gets the timing of events wrong. When a moving object passes behind a briefly flashing light, most people perceive the flash as occurring behind the object's true position at the moment of the flash. The brain seems to extrapolate the object's motion into the future, creating a mismatch between actual timing and perceived timing. Even more dramatically, the brain can sometimes reverse the temporal order of events. In what psychologists call the color phi phenomenon, two colored lights flashing in sequence can create the illusion of a single light moving from one position to another and changing color midway through its apparent motion. But here's the mystery. How can the brain know to change the color of the illusory moving light before the second light has actually flashed? By candors, you see. This suggests that conscious awareness of temporal sequence can be reconstructed after the fact, with the brain creating a coherent narrative from events that were initially processed out of order. Psychiatric conditions can severely disrupt temporal consciousness in ways that reveal its normally hidden mechanisms. Depression often involves what psychologists call temporal narrowing. The future appears foreshortened and hopeless, while the past becomes a source of rumination and regret. The normal, temporal perspective that allows planning and hope becomes collapsed into a painful, extended present. Anxiety disorders can create the opposite problem, an excessive extension of temporal awareness into a threatening future. People with anxiety often experience temporal hypervigilance, constantly scanning ahead for potential dangers and catastrophes. Time becomes experienced as an approaching threat rather than an unfolding opportunity. Schizophrenia can fragment temporal consciousness even more dramatically. Some individuals with schizophrenia report experiencing multiple timelines simultaneously or feeling that cause and effect relationships have become reversed. The normal binding mechanisms that create unified temporal experience appear to break down, leading to a fractured relationship with time that can be deeply disturbing. Dissociative disorders reveal another way that temporal consciousness can fragment. During dissociative episodes, people often report feeling like time has stopped or slowed to a crawl. The normal flow of experience becomes frozen, creating a kind of temporal limbo where minutes or hours pass without any sense of progression. Some describe feeling like observers watching their lives from outside the normal flow of time. Neurodegenerative diseases provide another window into time's neural basis. Alzheimer's disease progressively destroys the hippocampus and related structures that are crucial for temporal memory. As the disease progresses, individuals lose the ability to place themselves in time. They may think they're young again, fail to recognize the passage of years, or become confused about the sequence of life events. The dissolution of temporal consciousness follows the pattern of neural degeneration, revealing how dependent our sense of time is on specific brain circuits. Dreams offer perhaps the most common experience of temporal breakdown. In dreams, past and future can intermingle freely, causality can operate in reverse, and the present moment can stretch or compress in impossible ways. You might dream of having a conversation with someone who died years ago, or experience elaborate adventures that seem to last for hours but occur during a brief REM period. The temporal chaos of dreams suggests that our normal experience of linear time requires specific neural processes that are disrupted during sleep. The prefrontal cortex, which is crucial for temporal reasoning and sequence monitoring, shows reduced activity during REM sleep. This may explain why dreams feel temporally coherent while we're experiencing them, but often seem nonsensical when we try to remember them later. Psychedelic experiences can produce even more dramatic temporal distortions. Users often report time dilation so extreme that minutes feel like hours or years. Some describe experiencing their entire life history simultaneously, or feeling as though they've existed for eternity in a single moment. These experiences suggest that the neural mechanisms creating normal temporal flow can be temporarily dismantled, revealing alternative modes of temporal consciousness. Meditation can also lead to altered temporal states, though usually in gentler ways. Experienced meditators often report periods where time seems to stop or become irrelevant. The normal markers of temporal progression, thoughts, sensations, plans, and memories, can fade into the background, leaving awareness resting in what feels like an eternal present moment. These breakdowns of temporal experience, whether caused by illness, drugs, dreams, or contemplative practice, reveal that our normal sense of time is far more fragile and constructed than it usually appears. Time feels solid and reliable most of the time, but it's actually a delicate achievement of neural processing that can be disrupted in countless ways. Watch a young child at play, and you'll witness consciousness in a very different relationship with time than your own adult experience. Children seem to inhabit an eternal present, fully absorbed in each moment, without the constant awareness of temporal progression that characterizes mature consciousness. This isn't simply due to innocence or lack of responsibility. It reflects fundamental differences in how the developing brain constructs temporal experience. The journey from childhood's timeless awareness to adult temporal consciousness reveals how the brain gradually learns to construct the experience of time. This development isn't simply a matter of learning to read clocks or understand calendar concepts. It involves the gradual emergence of neural systems that create temporal self-awareness and the ability to project consciousness across time. In the earliest months of life, infants exist in what we might call pure, present consciousness. Without language to categorize experience or memory systems mature enough to maintain temporal sequences, babies live in a series of immediate present moments. They respond to hunger, comfort, and stimulation as they occur, but show little evidence of anticipating future needs or remembering past states. The Swiss psychologist Jean Piaget mapped the stages through which children develop temporal understanding. During the sensorimotor stage, roughly the first 2 years of life, children gradually develop what Piaget called object permanence, the understanding that objects continue to exist even when out of sight. This cognitive milestone is also temporal, involving the understanding that things persist through time even when not immediately present to consciousness. Language development profoundly shapes temporal consciousness. Different languages structure time in remarkably different ways, and children learning these languages develop correspondingly different temporal cognitions. English treats time as linear and quantifiable. We speak of spending time, saving time, and wasting time as if it were a commodity. Children learning English develop a correspondingly linear, quantity-based relationship with temporal experience. In contrast, some indigenous languages structure time very differently. The Piraha people of the Amazon have no words for exact numbers and no linguistic markers for precise temporal relationships. Their children develop a more cyclical, event-based relationship with time, rather than the clock-based temporal consciousness common in industrialized societies. The Aymara people of the Andes have a language that places the past in front and the future behind, the reverse of most European languages. They gesture forward when talking about past events and backward when discussing the future, reasoning that you can see the past because you know what happened, but the future is behind you because it's unknown. Children learning Aymara develop spatial temporal mappings that reflect this linguistic structure. Neurologically, the development of temporal consciousness parallels the maturation of the prefrontal cortex and hippocampus. The prefrontal cortex, crucial for planning and temporal reasoning, undergoes extensive development throughout childhood and adolescence, not reaching full maturity until the mid-20s. This explains why children struggle with long-term planning and why teenagers often make decisions that seem to ignore future consequences. The hippocampus, essential for episodic memory and mental time travel, also develops gradually. Young children can form memories, but these memories lack the rich temporal context that characterizes adult autobiographical memory. A 3-year-old might remember going to the zoo but have little sense of when this happened relative to other events in their life. This limited temporal context explains childhood amnesia, the inability of adults to remember much from their earliest years. It's not that young children can't form memories, but rather that they form them in a different temporal context. Without mature hippocampal systems to timestamp experiences, and without sophisticated language to encode temporal relationships, early memories exist in a kind of temporal limbo that becomes inaccessible to adult consciousness. The development of theory of mind, the ability to understand that other people have their own thoughts and perspectives, is intimately connected to temporal consciousness. Understanding that others have memories of the past and plans for the future requires the ability to project oneself across time and imagine different temporal perspectives. Children typically develop theory of mind around age 4, coinciding with major advances in temporal reasoning abilities. Cultural influences powerfully shape how temporal consciousness develops. In cultures that emphasize individual achievement and future planning, children learn to extend their temporal perspective forward, developing sophisticated goal-setting and planning abilities. In cultures that emphasize collective memory and ancestral wisdom, children learn to extend their temporal perspective backward, developing strong connections to family and cultural history. Technology is rapidly changing how children develop temporal consciousness. Digital natives grow up immersed in devices that fragment attention across multiple temporal streams, text messages, social media notifications, video content, and games all operating on different temporal scales. This environment may be creating new forms of temporal consciousness, with enhanced ability to process multiple temporal streams simultaneously, but potentially reduced capacity for sustained, linear temporal focus. The reminiscence bump phenomenon reveals something crucial about temporal consciousness development. Adults remember more events from their teenage years and early 20s than from any other period of their lives except recent years. This coincides with the period when the brain's temporal processing systems are reaching maturity while still maintaining high plasticity. The reminiscence bump might reflect optimal functioning of the neural systems that create temporal consciousness. Educational systems typically treat temporal understanding as a simple cognitive skill to be learned, focusing on calendar concepts, historical timelines, and schedule management. But research reveals that temporal consciousness is far more fundamental. It's the foundation for personal identity, moral reasoning, and meaning-making. Understanding how children develop this capacity could revolutionize how we approach education and child development. Autism spectrum conditions often involve differences in temporal processing that persist into adulthood. Many individuals on the autism spectrum struggle with temporal transitions, prefer predictable routines, and may have difficulty with temporal planning. These differences suggest that typical temporal consciousness development requires specific neural mechanisms that can develop differently in neurodivergent individuals. Trauma during childhood can severely disrupt the normal development of temporal consciousness. Traumatic experiences often become frozen in memory, disconnected from normal temporal processing. Children who experience severe trauma may develop fragmented temporal consciousness, with some memories feeling eternally present, while others become inaccessible. Therapeutic approaches increasingly recognize the importance of helping children develop healthy temporal consciousness. Play therapy often involves helping children process experiences across time, understanding cause and effect relationships, and developing realistic temporal expectations. Mindfulness practices, adapted for children, can help them develop present moment awareness while maintaining healthy temporal perspective. As you reflect on your own temporal consciousness, you might notice traces of these developmental processes. The way you experience time today reflects not just your current neural state, but the gradual construction of temporal awareness throughout your development. In quiet moments, you might still access something of the timeless present that characterized your earliest consciousness, not as regression, but as recognition of the multiple temporal modes available to awareness. If all moments exist equally in the block universe, if your entire life already exists as a complete four-dimensional structure in spacetime, what happens to free will? This question strikes at the heart of human identity and moral responsibility. If your future actions already exist somewhere in the fabric of spacetime, are you truly making choices? Or are you simply playing out a predetermined script written in the geometry of the universe itself? The tension between physics and free will has ancient roots, but modern scientific discoveries have given it new urgency. Classical physics, with its deterministic laws, suggested that if you knew the position and velocity of every particle in the universe, you could predict the future with perfect accuracy. The French mathematician Pierre-Simon Laplace imagined a hypothetical intelligence that could make such calculations, now known as Laplace's demon. In this deterministic universe, free will appears to be an illusion. Quantum mechanics seem to offer hope for rescuing free will by introducing fundamental randomness into physics. If quantum events are truly random rather than determined, perhaps this randomness provides the opening necessary for free choice. But random events are hardly more compatible with meaningful choice than determined ones. If your decisions result from random quantum fluctuations in your brain, they're not really your decisions in any meaningful sense. The block universe picture seems to make the problem even worse. If your future actions already exist as real features of spacetime, then the future appears fixed and unchangeable. Your sense of making choices moment by moment would be nothing more than the subjective experience of discovering what was already determined to happen. Free will becomes not just an illusion but a cruel joke played by consciousness on itself. Yet several philosophical approaches attempt to preserve meaningful choice within a deterministic or block universe framework. Compatibilism, the most widely held position among philosophers, argues that free will and determinism can coexist. According to compatibilists, what matters for free will is not whether your actions are determined, but whether they flow from your own desires, reasoning, and character. An action is free if it results from your own deliberative processes, even if those processes themselves are part of the causal structure of the universe. Consider the experience of making a difficult decision, choosing between job offers, deciding whether to end a relationship, or determining how to respond to a moral dilemma. During deliberation, you genuinely don't know what you'll decide. You weigh options, consider consequences, and struggle with competing values. The subjective experience of choice feels real and meaningful, even if the outcome might be determined by prior causes. The neuroscientist Benjamin Libet conducted famous experiments that seem to challenge free will. Using EEG to monitor brain activity, Libet found that unconscious neural activity begins several hundred milliseconds before people report becoming aware of their intention to move. This suggests that conscious will might be an afterthought, rather than the actual cause of action. However, Libet also found evidence for what he called free won't, the ability to veto actions after they've been unconsciously initiated. More recent neuroscience research has complicated Libet's findings. The brain activity he observed might reflect general preparation for movement rather than specific decision-making. The relationship between neural activity and conscious intention appears far more complex than Libet's original interpretation suggested. Consciousness might not initiate every action, but it appears to play a crucial role in coordinating, monitoring, and modifying behavior. The emergence of complex systems from simpler components offers another perspective on free will. Just as consciousness emerges from neural activity without being reducible to individual neural firings, free will might emerge from the complex dynamics of brain systems without being reducible to the deterministic interactions of particles. Emergence suggests that higher-level properties can have genuine causal power even when they arise from lower-level deterministic processes. Some philosophers argue that the block universe actually preserves rather than threatens free will. If all moments exist equally, then your choices at each moment are eternal features of reality rather than fleeting events that disappear into nothingness. Your decisions become part of the permanent structure of existence, giving them a kind of cosmic significance that purely temporal existence might lack. The relationship between knowledge and freedom adds another layer to these discussions. In the block universe, your future actions already exist, but you typically don't know what they are. This ignorance preserves the phenomenology of choice, even if the outcome is already determined. You must still deliberate, weigh options, and decide, because you have no access to the predetermined outcome. The process of choice remains meaningful even in a deterministic framework. Quantum mechanics introduces subtle complications to these discussions. While quantum randomness doesn't obviously help with free will, some interpretations of quantum mechanics give consciousness a special role. In these interpretations, conscious observation might actually help determine reality by collapsing quantum superpositions. If consciousness participates in creating reality rather than simply observing it, this might provide a foundation for genuine agency. The many-worlds interpretation of quantum mechanics offers yet another perspective. If every possible outcome of every quantum event actually occurs in parallel universes, then perhaps free will operates across the multiverse rather than within individual universes. Your choices might determine which branch of the multiverse you experience, even if all branches exist equally. Recent work in quantum biology suggests that quantum effects might play important roles in neural processing. Quantum coherence in microtubules, quantum effects in photosynthesis, and quantum entanglement in enzyme reactions all point to quantum mechanics operating in biological systems. While it's unclear whether these effects influence decision-making, they suggest that the brain might not be purely classical in its operation. The practical implications of these philosophical debates are profound. Criminal justice systems depend on assumptions about moral responsibility that require some form of free will. If free will is entirely illusory, should we abandon notions of punishment and desert? Alternatively, if belief in free will is necessary for moral behavior, should we preserve this belief regardless of its truth? Research suggests that beliefs about free will actually influence behavior. People who are told that free will is an illusion subsequently show increased antisocial behavior and decreased helping behavior. This suggests that belief in agency and responsibility plays important roles in human society, regardless of whether free will exists in some ultimate metaphysical sense. Perhaps the resolution lies in recognizing that free will operates at the level of experience rather than physics. Your sense of agency, your ability to deliberate and choose, your capacity to act according to your values, these remain meaningful features of human life, regardless of whether the universe is deterministic or probabilistic, block-like or flowing. In the gentle darkness of contemplation, you might notice both the sense of choice and the sense of inevitability that characterize each moment. Perhaps free will is not something you have, but something you are, not a property to be defended, but an aspect of consciousness to be explored and appreciated. In each moment of awareness, choice, and determination dance together in the mysterious space where mind meets reality. At the very beginning and end of cosmic history, time itself becomes strange and uncertain. The Big Bang marks what we call the beginning of time. But what could beginning possibly mean when time itself is coming into existence? And at the far future end of cosmic evolution, as the universe approaches maximum entropy and heat death, time may once again become meaningless. These temporal boundaries push us to the very limits of physical understanding and conceptual coherence. According to our current cosmological understanding, the universe began approximately 13.8 billion years ago in an event we call the Big Bang. But this wasn't an explosion in space. It was the emergence of space and time themselves. Before the Big Bang, there was no before in any meaningful sense, because time didn't exist. The very concept of temporal precedence breaks down at this cosmic boundary. The mathematical description of the Big Bang involves what physicists call a singularity, a point where the equations of general relativity break down and physical quantities become infinite. At the singularity, matter density and space-time curvature become infinite, and our normal concepts of causality and temporal sequence lose their meaning. This isn't merely a limitation of our current theories. It might represent a fundamental boundary where the concepts of space and time simply don't apply. Yet the idea of time beginning raises profound conceptual puzzles. In our ordinary experience, every event has causes that precede it in time. If the universe began, what caused its beginning? The traditional answer that God created the universe simply pushes the question back a step. What was God doing before creation? And what caused God to begin creating at a particular moment rather than some other moment? Some cosmologists attempt to resolve these paradoxes by proposing models where the Big Bang emerges from a prior state. Eternal inflation theory suggests that our universe is just one bubble in an eternally inflating cosmos. In this picture, the Big Bang represents the beginning of our local space and time, but not the beginning of existence itself. The eternal inflating background provides a temporal context within which our universe can begin. Cyclic cosmologies offer another approach, proposing that the universe undergoes endless cycles of expansion and contraction. In some versions, like the ekpyrotic universe model, our Big Bang represents the collision between multi-dimensional branes in a higher dimensional space. These collisions occur cyclically, creating an eternal sequence of universes with no ultimate beginning or end. But even eternal models face conceptual challenges. If the universe has existed for infinite time, we encounter what philosophers call the infinite regress problem. An actually infinite past seems to lead to logical paradoxes. If infinite time has already elapsed, how could we ever reach the present moment? These arguments suggest that the universe must have had a beginning, even if that beginning emerges from some prior state. Quantum mechanics adds another layer of mystery to cosmic origins. Quantum field theory shows that even empty space is filled with quantum fluctuations, virtual particles that pop into existence and quickly annihilate. Some physicists propose that the universe itself might have emerged from such a quantum fluctuation, tunneling into existence from literally nothing. The physicist Alexander Vilenkin has developed models where the universe spontaneously creates itself through quantum tunneling. In these models, the probability of the universe existing becomes calculable using the techniques of quantum mechanics. The universe doesn't need a cause in the traditional sense. It creates itself through the inherent creativity of quantum possibility. At the other end of cosmic time, the universe faces what appears to be an inevitable heat death. The second law of thermodynamics ensures that entropy continually increases, and the universe appears to be expanding and cooling toward a state of maximum entropy. In this far future, all stars will have burned out, all black holes will have evaporated through Hawking radiation, and the universe will consist of a thin soup of elementary particles at nearly absolute zero temperature. In this heat death scenario, time itself may become meaningless. Without energy gradients to drive irreversible processes, there would be no arrow of time. Without change and evolution, the very concept of temporal passage would lose its meaning. The universe would exist in a kind of eternal equilibrium where nothing happens and time effectively stops. Yet even this endpoint raises puzzles. Quantum mechanics suggests that given infinite time, random fluctuations will eventually recreate any possible configuration of matter, including conscious observers with false memories of a structured past. These Boltzmann brains would vastly outnumber naturally evolved observers, leading to the paradox we explored earlier. Some physicists propose that the heat death scenario might not be inevitable. Dark energy, the mysterious force driving the universe's accelerating expansion, might not remain constant forever. If dark energy decays or reverses, the universe might eventually recollapse in a big crunch that could potentially spawn a new cosmic cycle. Quantum gravity theories suggest even more exotic possibilities for cosmic beginnings and endings. In loop quantum gravity, the Big Bang might actually be a big bounce, the transition from a previous contracting universe to our current expanding phase. The apparent beginning of time would actually be the moment of maximum contraction, where classical concepts break down, but quantum geometry remains well defined. String theory and M theory propose that our universe might be one of countless bubble universes in an eternal multiverse. In this picture, individual universes can begin and end, but the larger multiverse structure is eternal. Time becomes a local property of individual universes rather than a universal feature of existence. The relationship between consciousness and cosmic time adds another dimension to these questions. If consciousness creates the experience of temporal flow, what happens to time in a universe without conscious observers? In the far future heat-death scenario, when the last conscious beings have died, does time continue to exist in any meaningful sense? Some philosophers and physicists argue that consciousness might be necessary for time itself to exist. Without observers to collapse quantum wave functions and create definite sequences of events, the universe might exist in a timeless superposition of all possible states. In this view, the origin of consciousness in the universe might also be the origin of time as we understand it. These cosmic questions about the beginning and end of time push us beyond the boundaries of scientific knowledge into realms where physics meets metaphysics. They remind us that time, which seems so fundamental to our existence, might be a more contingent and limited phenomenon than we usually imagine. As you rest in this moment between cosmic beginning and cosmic end, you might sense the profound mystery of temporal existence. You are a brief pattern of consciousness arising in the middle chapters of cosmic history, experiencing the flow of time in a universe where time itself has a beginning and may have an end. In this vast temporal context, each moment becomes infinitely precious, a unique occurrence in the grand story of cosmic evolution. Perhaps the most radical possibility suggested by our exploration is that consciousness doesn't simply experience time, it creates it. This idea turns our usual understanding upside down. Instead of consciousness emerging in time, time might emerge from consciousness. Rather than being passive observers of temporal flow, we might be the active creators of the very experience we think we're observing. This perspective draws support from several converging lines of evidence. Quantum mechanics suggests that consciousness plays a special role in determining reality through the measurement process. Neuroscience reveals that temporal experience is actively constructed by neural processes rather than passively received. And philosophy of mind points to the hard problem of consciousness, the mystery of how subjective experience arises from objective physical processes. The measurement problem in quantum mechanics has puzzled physicists since the theory's inception. According to the standard interpretation, quantum systems exist in superpositions of multiple possible states until they are measured. But what constitutes a measurement? And when, exactly, does the wave function collapse from multiple possibilities into a single actuality? Some interpretations of quantum mechanics give consciousness a central role in this process. In these views, conscious observation doesn't just reveal pre-existing reality, it helps create reality by collapsing quantum superpositions. If true, this would make consciousness an active participant in determining what becomes actual rather than merely possible. The physicist Eugene Wigner proposed that consciousness might be the factor that distinguishes measurements from other quantum interactions. In Wigner's interpretation, only conscious observation can collapse the wave function. This led to famous thought experiments like Wigner's friend, where the role of consciousness in quantum mechanics creates logical paradoxes that challenge our understanding of reality. More recently, physicists like Henry Stapp and Stuart Hameroff have developed detailed theories about how consciousness might operate through quantum processes in the brain. Hameroff and Roger Penrose propose that consciousness arises from quantum computations in cellular structures called microtubules. In their theory, consciousness emerges when quantum superpositions in these microtubules collapse, creating discrete moments of awareness. If consciousness operates through quantum processes, and if quantum processes are fundamental to reality, then consciousness might play a much more central role in the universe than we usually imagine. Rather than being a late-arriving accident in cosmic evolution, consciousness might be present at the most fundamental level of physics. This connects to philosophical positions called panpsychism, the view that consciousness is a fundamental feature of reality, present even in elementary particles. While this might sound far-fetched, panpsychism has gained serious consideration from philosophers and scientists grappling with the hard problem of consciousness. If consciousness is fundamental rather than emergent, it might indeed play a role in creating the temporal structure of reality. The relationship between consciousness and time becomes even more intriguing when we consider the binding problem in neuroscience. The brain processes information in parallel across many different regions and timescales, yet consciousness seems unified and coherent. How does the brain bind together disparate neural activities into unified conscious experiences? One answer involves temporal synchrony, neural oscillations that coordinate activity across different brain regions. Gamma wave synchrony, occurring around 40 times per second, appears to bind together different aspects of perception into coherent, conscious moments. These neural oscillations might not just reflect conscious unity, but actually create it by synchronizing otherwise separate processes. If consciousness emerges from temporal synchrony in neural networks, then consciousness is intimately connected to time from its very foundation. The binding of separate neural activities into unified awareness might be the same process that creates the unified flow of temporal experience. In this view, consciousness and temporality are two aspects of the same underlying phenomenon. The global workspace theory of consciousness, developed by Bernard Baars and later formalized by Stanislas Dehaene, proposes that consciousness arises when information becomes globally available across the brain. This global broadcasting creates a unified workspace where different neural subsystems can share information and coordinate their activities. But global broadcasting requires temporal coordination. Information must be integrated across time as well as across space. The creation of global conscious states might involve the same neural mechanisms that create temporal coherence in experience. If so, then the emergence of consciousness and the emergence of temporal experience are aspects of the same process. Recent research on the default mode network adds another dimension to these considerations. This network, active during rest and introspection, appears crucial for self-awareness and mental time travel. Its activity correlates with the subjective sense of selfhood, extending across time, the feeling that you are the same person who existed in the past and will exist in the future. Damage to the default mode network can disrupt this temporal self-awareness, leading to conditions where people lose the sense of psychological continuity across time. This suggests that consciousness doesn't just experience temporal extension, but actively constructs it. Your sense of being a self that persists through time is an achievement of neural networks rather than a simple recognition of objective temporal facts. Meditation and contemplative practices offer another window into consciousness's relationship with time. Advanced meditators often report states where the normal sense of temporal flow dissolves. In these states, described across cultures as experiences of eternal now or timeless awareness, consciousness seems to operate outside its usual temporal structure. These experiences suggest that the temporal nature of ordinary consciousness is not fixed or inevitable. Different states of consciousness involve different temporal structures. If consciousness can exist in timeless states, then perhaps temporality is something consciousness adds to experience rather than something it discovers in reality. The integration of information in consciousness appears to require temporal processes at multiple scales. From the millisecond timing of neural spikes to the second-scale integration of conscious moments to the minute scale. Construction of coherent experiences. Consciousness might create temporal experience by integrating information across these multiple timescales. Artificial intelligence research provides another perspective on consciousness and time. As AI systems become more sophisticated, researchers are grappling with questions about machine consciousness. Would an artificial conscious system experience time the way we do? Could consciousness emerge in systems with very different temporal dynamics than biological brains? These questions suggest that the relationship between consciousness and time might be more variable than we assume. If consciousness can be implemented in different substrates with different temporal characteristics, then the specific temporal structure of human consciousness might reflect the particular implementation of consciousness in biological neural networks rather than fundamental features of consciousness itself. As you rest in aware presence, notice how consciousness seems to create the very moment in which it exists. Awareness doesn't simply occur in time, it creates the temporal space in which experience unfolds. Past and future exist only as contents of present consciousness, and the present moment seems to be continuously created through the activity of awareness itself. If time is indeed an illusion, a construction of consciousness, rather than a fundamental feature of reality, how should this understanding change the way you live? This isn't merely an abstract philosophical question, but a deeply practical one that touches every aspect of human existence. The implications of timeless reality extend from how you relate to death and suffering, to how you find meaning and make moral choices in daily life. The recognition that all moments exist equally in the block universe can initially feel disturbing. If your entire life already exists as a complete structure in space-time, it might seem that nothing you do matters. Your struggles, achievements, and relationships would all be fixed features of an unchanging cosmic architecture. But this perspective, while intellectually coherent, misses something crucial about the nature of existence and value. Consider that in a timeless universe, every moment of joy, love, beauty, and meaning exists eternally. Your happiest memories aren't fading relics of a lost past. They're permanent features of reality, as real and present as they ever were. The love you feel for others, the beauty you perceive in nature, the satisfaction of creative accomplishment, all of these exist timelessly in the structure of reality. This eternal perspective can bring profound comfort in the face of loss and grief. When someone you love dies, the temporal illusion suggests they've moved from existence into non-existence. But the timeless view reveals that their life exists permanently in the fabric of space-time. Every moment you shared together, every expression of love, every meaningful interaction remains as real as it ever was. Death becomes not an ending, but a boundary, the edge of someone's world line through the eternal landscape of space-time. Yet, this comfort requires a fundamental shift in how you think about existence and value. Instead of valuing things because they persist through time, you learn to value them because they exist at all. The temporary nature of experience in the flowing time perspective gives way to appreciation for the eternal nature of experience in the timeless perspective. This shift can transform your relationship with present moment experience. If the present moment is all that truly exists, if past and future are mental constructions rather than real temporal locations, then presence becomes not just a spiritual practice, but recognition of reality's deepest nature. Mindfulness practices, meditation, and contemplative awareness reveal themselves as ways of aligning consciousness with the timeless foundation of existence. The ancient philosophical tradition has long recognized this timeless dimension of reality. Plotinus wrote about the eternal now, in which all time is contained. Medieval mystics described experiences of eternity that transcended temporal sequence. Hindu and Buddhist philosophy developed sophisticated analyses of how consciousness creates the illusion of temporal flow while resting in timeless awareness. These contemplative traditions developed practical methods for living from timeless awareness while functioning in the world of apparent temporal change. They recognized that while ultimate reality might be timeless, practical life requires engagement with temporal sequence. The challenge becomes learning to live from the eternal perspective while honoring the practical necessities of temporal existence. This balancing creates what we might call eternal ethics, moral reasoning that takes the timeless perspective seriously. In a block universe where all moments exist equally, moral actions don't just affect future outcomes, they create permanent features of reality's structure. Every act of kindness, every moment of compassion, every choice for love over fear becomes an eternal aspect of existence. This perspective can actually strengthen rather than weaken moral motivation. If your actions create permanent features of reality rather than temporary effects that fade with time, then moral choices carry even greater weight. The good you create exists eternally, but so does the harm. This recognition can inspire more careful, more compassionate choices about how to live. The relationship between timeless reality and personal meaning requires careful consideration. Meaning often seems to depend on narrative structure, the sense that your life tells a coherent story with development, growth, and purpose. If time is illusory, what happens to these meaningful narratives? One response recognizes that narrative structure might be a feature of consciousness rather than time itself. Even in a block universe, your world line through space-time has structure and development. The person you are now exists in causal relationship with the person you were and the person you will become. Growth, learning, and development remain meaningful features of your existence, even if they exist timelessly rather than temporally. Another response finds meaning in the eternal significance of conscious experience itself. If consciousness is the creator of temporal experience, then every moment of awareness participates in the fundamental creative process of reality. Your consciousness doesn't just observe the universe, it helps create the universe's temporal structure through the very act of aware experience. Practical implications of timeless reality extend to everyday concerns like planning, goal setting, and decision-making. If the future already exists, why plan for it? If outcomes are already determined, why make effort? These questions reflect confusion about the relationship between timeless existence and practical engagement. Planning and effort remain meaningful because they're part of the causal structure that creates the outcomes. Your future actions exist timelessly, but they exist as results of your present decision-making processes. The effort you make now is part of the eternal structure that includes your future achievements. Recognizing timeless reality doesn't eliminate causation. It places causation within an eternal rather than temporal framework. The experience of choice and agency remains valid even in a timeless universe. When you deliberate about decisions, you're discovering what choice exists eternally at that point in your world line. The experience of uncertainty and deliberation is part of the process through which eternal choices become manifest in consciousness. Free will might not require temporal becoming. It might be better understood as the eternal pattern of rational choice-making that characterizes conscious beings. Death takes on new meaning in the timeless perspective. Rather than being the termination of existence, death becomes a boundary condition, the edge of your particular pattern in the eternal fabric of reality. What you call your life is the complete four-dimensional structure of your existence in spacetime, and this structure exists permanently, regardless of which slice of it you currently experience as now. This can bring peace to the fear of death, while also highlighting the preciousness of conscious experience. Every moment of awareness is both eternal and unrepeatable. Eternal because it exists permanently in the structure of reality. Unrepeatable because consciousness can only experience each moment once as it moves through the eternal landscape. As you settle into the depths of this understanding, notice how it feels to rest in timeless awareness. The breath continues its rhythm. Sounds arise and pass away. Thoughts come and go. But the awareness in which all of this appears seems itself timeless, unchanging, eternally present. This awareness might be your deepest connection to the timeless reality that underlies the appearance of temporal flow. As our journey through the mystery of time draws to a close, we find ourselves not with definitive answers, but with a profound transformation in perspective. The question we began with, "Is time an illusion?" has led us through the labyrinths of physics, neuroscience, psychology, and philosophy, revealing that reality is far stranger and more wonderful than our everyday experience suggests. Einstein's revolutionary insights showed us that time is not the absolute, universal constant that common sense assumes. Instead, time reveals itself as relative, flexible, intimately connected to space in a four-dimensional fabric that can be stretched, compressed, and curved by matter and energy. The block universe perspective suggests that all moments, past, present, and future, exist equally in this eternal space-time landscape. Quantum mechanics added layers of mystery, revealing a realm where time's relationship to reality becomes even more enigmatic. At the quantum level, time appears not as a fundamental aspect of reality, but as an emergent property arising from more basic, timeless processes. The measurement problem and quantum entanglement hint at a reality where consciousness might play an active role in creating temporal experience. Thermodynamics provided time with its arrow through the second law and entropy's relentless increase. Yet even this seemingly fundamental temporal direction emerges from statistical principles and special initial conditions rather than from time's intrinsic nature. The universe's journey from order to disorder creates the temporal flow we experience, but this flow might be a feature of cosmic evolution rather than a fundamental aspect of existence. Neuroscience revealed that the brain is a sophisticated time machine, actively constructing temporal experience through multiple, interconnected systems. The feeling of time's flow emerges from neural processes that bind together past, present, and future into coherent conscious experience. When these systems break down through illness, injury, or altered states, time itself seems to fracture and dissolve. Psychology showed us how consciousness creates temporal experience through attention, memory, and predictive processing. The specious present, temporal illusions, and altered states of consciousness all point to time as a construction of awareness rather than an independent feature of reality that consciousness simply observes. The development of temporal consciousness in children reveals how the experience of time is learned rather than innate. Different cultures and languages create different temporal realities, suggesting that time's apparent universality might mask a deep plurality of temporal experiences. These discoveries raise profound questions about free will, moral responsibility, and the meaning of existence. If time is illusory and all moments exist equally, what happens to choice, growth, and purpose? We explored how these human concerns might be preserved even in a timeless universe through perspectives that emphasize eternal rather than temporal significance. The implications extend beyond abstract philosophy to practical questions about how to live. If present moment awareness aligns consciousness with reality's timeless foundation, then contemplative practices reveal themselves as ways of living in harmony with the universe's deepest nature. If every moment exists eternally, then each choice carries infinite significance. Yet perhaps the most profound insight from our exploration is that the question itself, is time an illusion, might be based on a false dichotomy. Time might be neither entirely real nor entirely illusory, but something more subtle and complex. Time could be real as an aspect of consciousness, while being illusory as a fundamental feature of physics. It could be constructed yet meaningful, emergent yet necessary. The timeless present moment in which you exist right now contains traces of this entire cosmic story. In this moment, the brain's temporal machinery is operating to create the experience of now. Neural networks are binding together sensory information, memory traces, and predictive models into coherent awareness. Consciousness is performing its mysterious alchemy of transforming physical processes into subjective experience. This present moment also exists as a specific location in the four-dimensional landscape of spacetime, connected through relativity's laws to every other event in cosmic history. It emerges from quantum processes that might themselves be timeless, arising through mechanisms that remain among nature's deepest mysteries. Most remarkably, this moment is conscious, aware of itself, and capable of contemplating its own nature. In you, the universe achieves the extraordinary feat of becoming aware of its own temporal structure. Through human consciousness, cosmic evolution produces beings capable of questioning the reality of time itself. This self-awareness might be more than mere cosmic accident. If consciousness plays a role in creating temporal experience, then every moment of awareness participates in the universe's ongoing creation of time. You are not simply observing the cosmic story. You are helping to write it through the very act of conscious experience. The ancient insight that consciousness and cosmos are intimately connected finds new expression in modern understanding of time's nature. Whether through quantum mechanics, where consciousness might collapse possibility into actuality, or through neuroscience, where awareness constructs temporal experience, consciousness emerges as a central rather than peripheral feature of reality. As you rest in this eternal moment, all of time's mysteries converge in the simple fact of awareness itself. Past and future exist only as contents of present consciousness. The flow of time reveals itself as the movement of attention through an eternal landscape. The universe's entire temporal evolution is somehow present in the timeless awareness that observes it. In the deepest recognition, the question, is time an illusion, transforms into the recognition that asking this question is itself a temporal process occurring in timeless awareness. The seeker of truth, the search itself, and the truth being sought all exist in the eternal present of consciousness. This is time's ultimate paradox and its deepest gift. In questioning time's reality, consciousness discovers its own timeless nature. In seeking to understand temporal flow, awareness recognizes its own eternal stillness. In exploring the mystery of when, consciousness awakens to the eternal now that it has always been. Thank you for joining this exploration into the deepest mystery of existence. Whether time flows or is eternally present, whether it emerges from consciousness or consciousness from time, whether it's fundamental or constructed, these questions point us toward the miracle of awareness itself, the presence in which all questions arise and in which all answers are found. Rest now in the timeless present, where every moment is eternal and every breath contains the entire universe. Sleep peacefully in timeless awareness.